Hello friends, welcome back to our channel. So in previous session we have seen different types of attributes like synthesized attributes and inherited attributes, and also we have seen different types of SDTs. So L attributed SDT and S attributed SDT. Now in this session will see one more concept in compiler design, that is annotated parse tree, which is an output of the second phase, that is semantic analyzer. So annotated parse tree. So here the parse tree is completely different with the annotated parse tree. Alright. So from the first phase we'll be getting the lexemes, and then in the second phase we'll be getting the parse tree, and the third phase in the semantic analysis we'll be getting the annotated parse tree. So we have seen for every non-terminal there will be an attribute or a value. Okay, so the parse tree which will be having only the non-terminals and the terminals, where leaf nodes are the terminals and intermediate nodes are the non-terminals. So annotated parse tree means for every non-terminal, that means for every internal node, it will be represented with the attribute. So the attribute can be anything. It can be a value, or it can be a type, or it can be a reference, anything. Okay, now we'll see one example for this annotated parse tree. So let us take an example, annotated parse tree generation for some 10 into 5 plus 3. So we know what is the evaluation of this one. So the result will be, the multiplication will be done first, because the highest precedence will be there for the multiplication among the into and plus. So 50 plus 3, so it becomes 50 plus 3, which is a result called a 53. So if the expression, I mean, this is represented with id into id plus id. So we need to construct the parse tree for this particular expression, where for every non-terminal will be representing the value. So once executing this one, we should get the result as 53, where first id is replaced with a 10, second identifier is replaced with a 5, and the third identifier is replaced with a 3. Now we need to construct the annotated parse tree for this one. So parse tree for this one and annotated parse tree for this one. Okay, so the productions, first let us see the productions. What are the productions which satisfies this particular expression? So E tends to E plus T, E tends to T, T tends to T into F, T tends to F, and F tends to ID. So these are the productions which satisfies this particular expression. So for this one we need to write the semantic rules. Semantic rules. So we know the SDD, syntax directed definition, is a combination of production and semantic rules. So here everything is a value. Okay, everything is a value. We are not using any kind of data types or a memory, right? So for everything is a value. So semantic rules will be E dot value, the attribute we are representing with a dot value. So E dot value is equal to E dot value plus T dot value, and this one E dot value is equal to T dot value, and for this T dot value is equal to T dot value into F dot value, and for this T dot value is equal to F dot value, and for this production F dot value is equal to, so this is an identifier, not a non-terminal, so this will be directly having id dot lex value. Lex value means a direct value. So for these semantic rules, first we will need to draw the parse tree. So parse tree means deriving this particular definition. So we have to start from start symbols. For production we know E is a start, so E, it can be expanded with E plus T. So the second one is a addition, first one is a multiplication. So this can be changed to T, which further can be expanded with a T star F, and T can be expanded with F, which is an ID, and F, which is an ID, and T F, which is an ID. So this is a parse tree. Okay, this is a parse tree for the given string. So you can observe these are all internal nodes. These are all internal nodes, and all the leaf nodes are the terminals. You can see. So all the leaf nodes, what are the leaf nodes? ID, which is a terminal, ID, which is a terminal, star, terminal, plus terminal, ID, terminal. So leaf nodes are the terminals, and intermediate nodes are non-terminals. Now, what is an annotated parse tree? Annotated parse tree. So if you represent, so what we are saying, so you can observe here, every non-terminal will be having a different attributes. See, for example, if you take E, so E can have a value, E can have a data type. Okay, E means a memory variable, so it can also be have a memory. So like that, there will be a lot of attributes, but in this particular example we are showing that every non-terminal is having only a value. So if you want to get this one, that depends upon E dot value and T dot value. So if the LHS part is completely depends upon RHS part, that we are calling it as synthesized attributes. So this is a completely example for the synthesized attributes. Okay, now annotated parse tree, this is a parse tree which we need to represent each and every non-terminal with its attribute, that may be either value or type or memory, whatever it may be. But in the annotated parse tree, every non-terminal should be represented with a corresponding attributes based upon the semantic rules. So here we will write here, I will write once again a parse tree. First we will write the parse tree, then we will convert into annotated parse tree. So this one is a T, which again further divided as T star F, and again F, ID, F, ID, F, ID. See here you can observe some productions like this one and this one, we are having some left recursion, but we don't worry about the left recursion because we are using the bottom-up approach. So if you are using the bottom-up parsing, we have studied that there will be no problem with the left recursion and left factoring. So no need to worry about that one. So here we are using the bottom-up approach. So bottom-up approach means we need to travel to the bottom first. So this is a leaf node. So what happens? ID. So what is the value of this ID? Okay, so it is id dot lex value. So this becomes id dot lex val. Okay, and coming to this F, so you can observe the last one, id dot lex value can be represented with a F dot val. So the F dot val depends upon its child. So here F dot val is equal to id dot val, lex val. Okay, sorry, is equal to id dot lex val. And see, you can observe, and this particular T, value of T depends upon its child F. So here it will be T dot val is equal to F dot val. So what happens? This value will be occupied in this position and this value will be occupied in this position. And if you want to consider this particular non-terminal T, that depends upon the child T and F. So we need to travel in this way. So id, again we are getting id is equal to id dot lexval. So f dot val is equal to id dot lexval. Okay, now what about this value? So this value is t dot value is equal to the value of left child and the value of right child. So this becomes t dot value is equal to t dot value into f dot value, because here we are having a into operation, and this value can be replaced with this one. So e depends upon its child, e depends upon its child. So here e dot value is equal to t dot value. So what happens here? It is id dot lex value, the first one, it is a 10, and id dot lex value it is a 5, and here we'll be getting 10 into 5, 10 into 5 is equal to 50. The value is 50, and here we are getting the value 50. Here we are getting the value 50. Now again see what happens. So it moves upwards, and again it comes here id. So again it is id is equal to id dot lexval. id dot lexval. id dot lexval is the third one, that is a 3 here. Now f depends upon id. According to the productions, f is equal to id lex value, id dot lex value. Yes. So f dot val is equal to id dot lex val. So what happens here? 3 will be getting, and here again t dot val is equal to f dot val. So what is f dot val? It is again 3. So what happens here? E. So e dot val is equal to e dot val plus t dot val. So what is the value of here? E dot value is a 50 plus here it is a 33. So which gets 53. So is equal to 53. So 50 is equal to, here we will be getting a 53. Okay. So this E depends upon these two attributes. I mean these two children, E and T. So hope you understood. This is a parse tree. Okay. So this representation is a parse tree, but this representation is an annotated parse tree. So annotated parse tree means for every non-terminal should be represented with its attribute. That may be either value or type or memory. That depends upon the semantic rules and the example. So also this will give you the order of evaluation, how it will be evaluated. You can see in this example, first the 10 into 5 has been done, and that is added to the rest of the id, that means a 3 in this example. Okay, so this is a difference among the parse tree and annotated parse tree, right? So parse tree is an output of syntax analysis, and annotated parse tree is the output of semantic analysis. Okay, and the implementation of this particular SDD, we call it as a syntax directed translation. So as here all the productions are synthesized attributes. Here you can see in the semantic rules, every attribute, I mean every non-terminal is represented with a value. So and also the LHS is completely depends upon the RHS. The parent completely depends upon the children. So how we are getting the parent value from the children value? So that's why we are calling it as a synthesized attributes, and this is a synthesized SDT. Yes, attributed SDT. And finally, this is the annotated parse tree. You can feel the difference among parse tree and annotated parse tree. So hope you understood this one. And if you are having any queries regarding this one, feel free to post your doubts in the comment section. Definitely I'll try to clarify all your doubts. If you really enjoyed the session, like my session, share my session with your friends, and don't forget to subscribe to our channel. Thanks for watching. Thank you very much.